I am Barry Duggan, KV4FB. I'm presenting a modular transmit receive station control based on my repository in Duggan GRCon21. My design criteria is that I wanted a plug and play setup where I could create different modules working together, a control, a transmit, a receive, and a relay driver. The USRP source and sync blocks must be in the same process for them to work, sharing the services, same flow graph. All transmit and receive modules must have the same interface to the control module. That seems intuitively obvious. If you want all the GUI presentations on the same display screen, the control module, transmitter, and receiver should be in the same computer. Otherwise, you'd have two different monitors to look at. And very important to me, no hardware modifications should be required. There are three branches in my repo. The main, which is the default, is my development branch. It uses flowgraphs for GNU Radio 3.9 plus and includes relay control using a Raspberry Pi computer. The main 3.9 uses a USRP and the sample rate is set to 768 kilohertz. The main 3.8 is aimed at lower speed and uses a Pluto, and the sample rate is set to 576 kilohertz. And I was hoping it would run on a Raspberry Pi. And note that the Mate 3.8 and the Mate 3.9 only simulate the relay switching. Only the main branch has the real relay switching in it. Here is an overview of the data flow. And starting with the antenna here, the receive side comes through the antenna switch through a USRP B200 mini into the transmit receive switch module and then goes to a receiver module. On the transmit side, data from the transmitter module goes through the transmit receive switch through the B200 mini, through a power amplifier, and then to the transmit receive switch and the antenna. So part of the switching process sends a signal to the Raspberry Pi to switch the antenna relay and to switch the power to the power amplifier. So now let's see how that looks on the flow graph for the transmit receive module. I'll trace those same stream paths. The receive side USRP source goes through a mute block and to a pub sync. And then on the transmit side, data from the transmitter comes in through a sub source and through a selector, which is acting like a mute block, a low pass filter, and then to the USRP sync. The rest of this in the middle is the transmit receive switching logic. And notice it is all done by messages rather than streams. The toggle button sends a message to the transmit receive control, which is a embedded Python block. And then messages go to the various functions here. Now the reason for doing the mute up here and the selector down here, when you do a mute block, when you set it to mute, it continues to stream zeros on the output, which is fine for a receiver. On the transmit side, I needed something that actually stops the output, and the selector will do that. When I disable the selector, the output is nothing rather than being a stream of zeros, and that causes the USRP sync to stop transmitting. Now let's look at the switching sequence for this. The Python transmit switching sequence is to mute the receiver, turn off the receive LED, turn on the antenna LED, and then send a message to the relay controller to ask it to do the switching. Wait for the reply message, delay another 10 milliseconds, and then unmute the transmitter. So in the Raspberry Pi relay controller, there is a straight Python program, and it waits for an input message. And then if it's told, this is the transmit sequence, switches the antenna from receive to transmit, delays 100 milliseconds, turns on the power amplifier, delays another 250 milliseconds, and then sends a message back to the client, which was the transmit receive package. Now these delays are unnecessarily long, but the reason I did them this way was so I could visually observe the switching sequence. You can see and hear the relays go click, click. Here is a picture of my RPi 3B+, with the relay board mounted on top of it. And this is in the transmit state. There's actually an LED right here, and another one here for the two relays that I have turned on. And it has jumper wires. There are actually jumpers on this block right here, but they use some pins that are dedicated to other functions. And I wanted to use pins that had no dedicated function. So I pulled the jumpers off this block and put in the wires to pick up the pins I wanted. Now here is the GUI for the transmit receive module. Receive LED, antenna, power amp, receiver gain, transmitter gain. Now to set a receive frequency, you actually key into this field right here with the frequency you want. And then if you're working into a repeater like this 9.4 repeater we have, you can set the offset appropriately. And then the transmit frequency is calculated, receive frequency plus minus the offset gives the transmit frequency. And here's the transmit button. So when you press the transmit button, this is what you see after it's finished switching. Receive off, antenna switched, power amplifier on, and the transmit button turns red to remind you that you are actively transmitting. Now I currently have 3 receiver modules in the package: narrowband FM, single sideband, and just for fun, a broadcast wideband FM stereo. Also lets me check out the antenna and make sure everything else is working. And good, relaxing fun. The single sideband receiver is this particular module uses the Weaver method. You've heard of the filter method and the phasing method, and sometimes Weaver is called the third method. And this is it, where actually the BFO is injected into the signals in the middle of the audio passband. So it take the real part and multiply it times the cosine signal, and take the imaginary part and multiply it times the sine signal. And then you either add or subtract the two to get the sideband you want. So there's a sideband switch here. This chooser right here will affect this multiplied by +1 or -1. And it works really well. The transmit modules, I have a narrowband FM transmitter and a single sideband transmitter. Here's the flow graph for the narrowband transmit. And it has 2 interesting features to it. One is I'm using GRCESSB, which means controlled envelope single sideband, was what it was designed for, but it works well for narrowband FM as well. So it has a magnitude clipper and a peak stretcher, and then filters, more filters, more filters. So that signal comes down to here, and I cut off the low end at 200 hertz, and then I add in PL tone. And so if you're using repeater and it needs a PL, there is a chooser for all of the popular PL tones, 23 of them, I think, something like that. So add those 2 and then transmit, upsample, and send that to the transmit receive control module. Here is the GUI for the FM transmit, mic gain, output level, and as you can see, the envelope doesn't have any real sharp spikes to it. It's much smoother, but the sound is excellent, and it gives you a much higher average voice power than without having that controlled envelope speech processor in there. And also have a loopback test that can be used in place of the transmit receive control. So it takes the transmit signal, low pass filter, a throttle, which you can set the sample rate to whichever you're using, and then sends it to the receiver module. So by setting it up with just a transmitter, receiver, and the loopback, you can do testing without the hardware in it. So in summary, it's easy to add new modules. I'm thinking about adding my radio teletype, which is another repo, and my Morse code transmitter, which is one of my other repos. And then also I'm looking at doing a BPSK with hardware, or a QPSK with hardware, or maybe both, and integrate them with this package. So it's easy to test variations. It's easy to test new modules. Thank you for your time.